Hello. So this video is intended to replace a missed class that will be not happening, so to speak, on Thursday, November 6th, 2025. The reason is that because I will be in San Luis Obispo at the Cal Poly campus talking about AI on a panel at AI convening that they're holding down there. But I did want to make up for that class with a video, and so that's what this is. This is here today. We're going to be talking about how the first derivative relates to the increasingness or decreasingness of a function, a concept which we'll collectively call the monotonicity of a function. I know it's a fancy word, but that's what we call it. And how the second derivative relates to something called the concavity. So hopefully yesterday we began talking about things like critical points. We started talking about local extrema and the like. Um, Hopefully you have this document that printed out for you because I handed this out on Wednesday. And we've talked about this concept of a critical point. We've talked about local extrema, local minima, local maxima. And we talked about doing this thing called a sign analysis. Okay. So I'm going to take all of that for granted here today, that we know how to do this idea of a sign analysis and that we know how to interpret it to apply the first derivative test to analyzing the critical points of a function, determining whether or not they are local minimum, local minima, local maxima, or neither. So I'm going to presume that knowledge exists. And basically, if you want to review, you need to reread section 2 of this handout. However, today I want to talk about section 3 of this handout. And I want to talk about the concept of, again, of monotonicity. And you can read here that this is just a fancy word referring to whether a function is increasing in value or decreasing in value as we observe the input x grow. So, I mean, I want to walk through these definitions because one of the characteristics of mathematics that you should come to appreciate, I hope, is that mathematics is very, very precise. And when I say that, I mean that um, it when mathematicians make definitions, these definitions should not be fuzzy. There's no fuzziness allowed. Precision is something that characterizes mathematics. And so we all know how sometimes language can be very, very hard to interpret. There can be ambiguity in meaning. Mathematicians strive to prevent that from happening. And so sometimes this requires some very, very, very difficult to understand or difficult to parse definitions. And the definition I'm about to give you for increasingness and decreasingness is of that character. But really, the underlying idea, when you think about carefully what these definitions are saying, and you really like devote your best brain cells to thinking about it, I think the picture becomes kind of clear about what it is, and it's a very intuitive picture. So I want to share that with you. So definition, first of all, suppose f is a function which is at the very least defined on some open interval, which we'll call a comma b. Okay, so recall this is the collection of all points or all real numbers greater than a but less than b, and where we exclude a and b. Yeah. Okay. So suppose f is a function defined on this open interval, then we say f is increasing on a comma b. So I'm defining this concept here. F is increasing on a comma b if for all x1 and x2 that we draw from this interval. So for any two numbers that live in this interval. This little pitchfork symbol just means that these are what are called elements of this set of numbers. If x1 is less than x2, okay, so if it happens that the smaller of the two numbers that we've drawn from this interval is x1, then f of x1 is less than f of x2. Shoot, my mouse is in the way here. Sorry, my desk is a mess. I maybe can't even see that, but that's good. So that's good. You can't tell. If you're following along and you're wondering what the hell I just wrote, it's written right here. Okay, exactly what I just said. Or almost exactly, yeah? The picture here is very straightforward. An increasing function is one for which, if I draw its graph, it looks something like this. Here's an increasing function. Why? Because for any x1 and x2 that I choose, if x1 is to the left of x2, then I can look at f of x1. This would be f of x1 right here. And don't you agree that f of x1 is smaller than f of x2? Think about the y coordinates that these correspond to. F of x1 in this picture looks negative. F of x2 looks pretty positive. Yeah. All this is saying is that when you read from left to right, you see the values of the y coordinates increasing. That's it. That's all that's being said here. This is an increasing function, however. Okay? This is increasing. What on earth does decreasing mean? Well, the picture, I think, let me draw the picture first and then define it, I think is pretty sensible. Here's a decreasing function. Take any x1 and x2. Here's maybe an x1. Here's maybe an x2. Look at f of x1. That's the y coordinate of the point on the graph. And look at f of x2. That's the y coordinate of this point on the graph. And agree with me, please, that f of x1 is greater than f of x2. Indeed, that's the definition. So this is a decreasing function here. Let me now define it. We say f is decreasing on the interval from a to b if for all x1 and x2 in a comma b, if x1 is the smaller of the two, then f of x1 is bigger than f of x2. This is the fancy way, the mathematically rigorous way of defining the intuitive concept that when you read from left to right, you see the values of y increasing or decreasing. I hope that's clear. Okay, excellent. Now, maybe I'll make this comment. A function is allowed to have regions or intervals on which it is increasing at the same time as having other intervals on which it is decreasing. So, for example, you could have a function that looks something like this. Okay, here is a function. Let me, for the purposes of this discussion, say that this point here, its x coordinate is going to be called, I don't know, p, and this point here will have x coordinate q. Here are some true statements. From negative infinity to p, f is increasing. Okay? And you can see that from negative infinity out here all the way up to p, the values of the y coordinate are getting larger and larger and larger as we read from left to right, hence increasing. Between p and q, f is decreasing. Also a true statement. Same f, but when we specify a different interval, we have a different quality in its monotonicity. And finally, from q to infinity, f is increasing again. Okay? Is every function increasing or decreasing on a specified interval? No, there can be a mix. And in fact, it's possible for a function to not be increasing or decreasing on any interval. So, for example, if you look at this function, the good old constant function, or a good old constant function, one whose graph is a horizontal line, then and we say declare this is f of x equals 5. Okay, a constant function. No matter what this function eats, it always spits out 5. Then we say that on the interval from negative infinity to infinity, f is neither increasing nor decreasing. Neither increasing or decreasing. Sometimes people write nor decreasing. It means same thing. Okay. Yes? Yes? All right. Now, one thing I want you to observe, okay. Now the question is, how can we, based upon a formula for, let's say, f of x, like, you're very often given like f of x equals x squared plus 3x plus sine of x. How can we, on the basis of a formula for the output of a function, determine on what intervals that function is increasing and on what intervals it is decreasing? Well, the key thing is a technique that we've already learned called sign analysis. Why? Because I want you to notice something about the intervals on which f is increasing and decreasing. Let's look at this interval from negative infinity up to p for this function. Do you notice that when we look at the tangent lines to this function, there are all sorts of different tangent lines, but they all have something in common. They're all positively sloped. They're all positive sloped lines. Look over here on the interval from q to infinity where we said f was increasing. Over here, also increasing. Positively sloped tangent lines. Yeah? Whereas in between, on the interval on which it's decreasing, the function is decreasing, we see in the graph negatively sloped tangent lines. Yeah? So negative slope. And over here, positive slope. I should say slopes, because there's many slopes here. So this is pretty strong evidence that the sine of the slope of the tangent line, and remember this, when I say sine here, I'm using the word S-I-G-N, not S-I-N, the trig function. Not that. The sine, is referring to the positiveness or negativeness of, in this case, the slopes of tangent lines. So what I'm saying is that the sine of the slope of the tangent line is correlated strongly with whether or not the function is increasing or decreasing. Notice that in this example, where f is neither increasing nor decreasing, the tangent lines are funny in that they're all just horizontal. Remember what the tangent line is. The tangent line is what you get when you zoom in on a particular point on the graph. Remember? If you take a point on this graph, you plot this graph in Desmos, this curve, and then you zoom in on that curve, closer and closer and closer. For well-behaved functions, you are going to see a line. And that line, that's the tangent line. Now, imagine zooming in on this horizontal line here. What you're going to see is just the horizontal line. Does that make sense? And so its slope is 0. The sine, S-I-G-N, of 0 is neither positive nor negative. And that's sort of an indication that this function is neither increasing nor decreasing, because we're saying, again, important idea, that the increasingness or decreasingness of f is tied to the sign, S-I-G-N, of f prime. This is summarized in this document in this box. And you'll want to remember the idea behind this box. The idea behind this box right here is exactly what I just said. And I'm going to say it again. So open up your earballs, okay? The short way of saying it is that the monotonicity of f is determined by the sign of f prime, the derivative. Suppose f is differentiable on AB. All that means is that the derivative exists on this interval from A to B. If f prime is positive, that's what this sign here means. Remember, the alligator preferring to eat this over 0 means that this, the f prime of x, must be positive. If this is true for all x in the interval from A to B, then f is increasing. Positively sloped tangent lines means increasing. Okay? If f prime is negative, on the other hand, then f is decreasing. Don't get it twisted, okay? You have to understand. The sign of f prime tells you about the increasingness/decreasingness, namely the monotonicity of f. The sign of f prime tells you about the monotonicity of f. The monotonicity of f is determined by the sign of f prime. The monotonicity of a function is determined by the sign of its derivative. Okay, so let's see an example of this in action. A really simple example, shall we? Doc, ham, and face. There we go. So, for example, suppose that we have f of x equals, how about 1/2 x squared plus 2x plus 3. I'm just really making things up. I don't know what I'm doing. Okay. Now, maybe you know that since this is a quadratic polynomial, it is a quadratic polynomial, that its graph is going to be a parabola. And we're interested in figuring out where that parabola represents an increasing function and a decreasing function. And we're going to see that this is represented by a mix of the two. To understand, and here's the question that I want to ask. Let's analyze the monotonicity of f in this case. So what do I mean when I say this? This is just another way of saying find intervals on which f is increasing and f is decreasing. So you notice that this is a lot of writing. So the way that I'm going to do this in the future is just say analyze the monotonicity of f. And what am I expecting you to do here? Well, I'm expecting you to use this box. That the monotonicity of f is determined by the sign S-I-G-N of f prime. Did I say that right? I don't know. Let me say it again if I've got it wrong. The monotonicity of f is determined by the sign of f prime. So evidently, we should look at the sign of f prime. Well, first of all, what's f prime? F prime, if I take the derivative of this, the 2 comes down and gets married to the 1/2, and I just left with an x. I have x plus 2. What could be easier than x plus 2? Not much. What does x plus 2 look like? It looks like a line of slope 1 with y-intercept 2. Slope 1 comes down like this, goes up like that. You might ask yourself, what's the x-intercept of this line? And it turns out that it's at -2. Why? Because when you plug in x equal to -2 here, you get 0. This, don't get it twisted, is the graph of f prime, not the graph of f. The graph of f is a quadratic parabola. This is not a parabola, this is a line. But what can we learn about the parabola from the graph of f prime? Well, we see that because when we are to the left of -2, so over here from -infinity to -2, f prime is negative. And the sign of f prime determines the monotonicity of f. What this means is that f is decreasing on this interval from -infinity to -2. Okay? This is a deduction that we make. The fact that f prime is negative implies, that's what this double arrow saying here means, implies that f is decreasing on this interval. Similarly, we see with our eyeballs that because f is positive on the interval from -2 out to infinity, and why is it positive? Because the portion of the graph of f prime, which is corresponding to values of x which are greater than -2, we see that the function is increasing, or we see that the sign of f prime is positive. That therefore we can deduce that the function f is increasing. So on the interval from -2 to infinity, f is increasing. F prime is positive. That's what I want to say. And therefore, by the comments we made before, this implies f is increasing on the interval from -2 to infinity. Sorry, this isn't well organized, but hopefully you can follow. So these are all comments about f prime. We've now deduced something from f prime, the sign of f prime. We've deduced something about the monotonicity of f. And we could draw a graph of f based on this information. Here's what that graph, I believe, will look like. Yeah, 4, 2, -2. So I think it would look like this. And it would sort of be kind of a wider kind of parabola like this and like that. And this is -2. And the thing that I want you to observe, and you should Desmos this actually, just to verify, because I'm really winging it here. But I believe that over here, f, you'll notice that f is decreasing over here. From -infinity to -2, and over here, f is increasing. Okay? Right. So if we wanted to give the boxed answer to this request to analyze the monotonicity, I would say f is increasing. I'll just write f is inc for now on the interval from -2 to positive infinity, and f is decreasing on the interval from -infinity to -2. And I box that as my summary answer. Okay? That's me analyzing the monotonicity of f. Monotonicity of f is determined by the sign of f prime. Memorize this. Okay. And so you see that it is crucial that we learn how to do and we get good at doing the sign analysis of functions. Because based on what we just learned, we see that the sign analysis of a function, which will tell us when a function is positive and when a function is negative, if we apply that sign analysis to f prime, then we learn the monotonicity of f. We learn on what intervals f is increasing and on what intervals f is decreasing. I give you in section 4 here a step-by-step process to find the sign analysis of a random function h. Let's look at this. sign analysis of h. The objective here is to find intervals on which h is positive and intervals on which h is negative. Okay? I give you a 5-step process here. Step 1. Find the zeros of h. Oh, I should have wrote of, but I didn't. My bad. Find the zeros of h and the location where h fails to be continuous. Divide the domain of h into intervals using the points found in step 1. So we're going to take, the way I'm going to envision this, we're going to take the real line and cut it up into pieces. Where are we going to make the cuts? We're going to make the cuts at those points that we found in step 1. The places where the function is either 0 or discontinuous. We are going to pick a random point inside each interval that we found in step 2. And then we're going to evaluate the function at each of these test points and figure out what the sign is. Based on that, we're going to conclude that either h is positive or negative on the entire interval containing the test point. Okay? So hopefully I've done a little bit of this on Wednesday so that you're not completely in the dark about this. But let's do this sign analysis for a fairly complicated function. And here's the example that I give you in the in this worksheet here. 2x times x squared plus 3 divided by x squared minus 1 cubed. It's horrifying looking, okay? And it might not be at all obvious where this function is positive and where it's negative, right? Like if I was to ask you on what intervals is this function positive and on what intervals is this function negative, that would be quite a challenge to figure that out. But that's what sign analysis hopes to accomplish. Okay? So I'm going to just walk through this with you. So here's my function. It's 2x times x squared plus 3, okay, divided by x squared minus 1. Step 1. Let's find all the values of x where h of x is 0 or discontinuous. A function like this, which is a fraction, in this case this is what's called a rational function, is 0 precisely when the numerator is 0. Although what could happen, there is an exception, is that if the numerator and the denominator are simultaneously 0, then that can cause the entire fraction to be undefined, right? So we're not talking about places like that. That would be a discontinuity. But in any case, we see that we're going to have to analyze when that numerator there is 0. Okay, when is the numerator 2x times x squared plus 3 equal to 0? Well, that happens when x is equal to 0. That makes this factor 2x equal to 0. Yeah? When is the factor x squared plus 3 equal to 0, however? Well, hopefully what you understand from your pre-calc is that this is in fact a situation where the function is never 0. For example, if I was to graph for you x squared plus 3, just all by itself, x squared plus 3. If I was to graph this for you, well, it looks like the standard smiley face parabola, you know, like y equals x squared. It looks like that one, except translated 3 units upward. That's by virtue of the plus 3. So it would look like this. There's 3, and it would go up, 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 up like this, and go up, 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 up in this direction. Okay? And in particular, it's very plausible that you see this parabola never intersects the x-axis. And hence, x squared plus 3 is never 0. So because this parabola never intersects the x-axis, x squared plus 3 is never 0. There is no value of x, which makes x squared plus 3 equal to 0. And that kind of stands to reason, for the following reason. No matter what x you pick, x squared is always either 0 or positive. It is never negative. You can never square something and get a negative number. Or rather, you can't do that. I can do it, but you can't. So effectively, we can't, okay? X squared plus 3 is never 0. Because if you take something like x squared, which is either 0 or positive, and then add 3 to it, well, that's always going to be strictly positive. You feel what I'm saying? We can see that graphically by the fact that it doesn't intersect the x-axis. Okay. Another way that you can detect this kind of state of affairs is by looking at what's called the discriminant of this quadratic polynomial. And I'm going to mention this now because it turns out to be important, maybe not so much right now, but later on for sure. Just a quick reminder, if you have ax squared plus bx plus c, this is a quadratic, the discriminant is b squared minus 4ac. Now that should feel familiar to you because that's the thing that lives under the square root in the quadratic formula. And now remember that if b squared minus 4ac is positive, then the quadratic polynomial has two distinct roots. Distinct real roots. Remember this from your algebra class, I hope? If b squared minus 4ac is equal to 0, then ax squared plus bx plus c has a repeated root. And finally, if b squared minus 4ac is negative, because you can't take the square root of a negative number, has no roots. No zeros. Roots and zeros are synonyms, okay? Why do we have two words for the same thing then? Roots are often used in the context of polynomials, and zeros are used more generally for functions. Why not call the things in functions roots? Great point. Why am I not defending it? Because I can't. It's just the stupidity of words, okay? Words are stupid like that. And we just have to get used to it. This is all sensible. I don't have this like table memorized. I just know it. And the reason I know it is because it all comes from the quadratic formula. If b squared minus 4ac is positive, then remember we have that plus or minus square root of a positive number. So we get the two roots from the plus and the minus, something which is well defined. If b squared minus 4ac is 0, though, then we're taking the square root of 0 in the quadratic formula. Plus or minus 0, that's the same thing. You see what I'm saying? And finally, if b squared minus 4ac is negative, well, we know we can't take the square root of a negative number, or rather, you can't take the square root of a negative number. I can, but you can't. And so for that reason, as far as you're concerned, this quadratic polynomial would have no roots. Okay? So all of this is just a quick review of some basic algebra, but I want to say it out loud so you remember it. All of this applies to x squared plus 3, because if you compute the discriminant, you're going to see you're in this third case. B is 0, A is 1, and C is 3. So the discriminant, I believe, is negative 12. Negative 12 is negative, so ax squared plus bx plus c, which is x squared plus 3 in this case, has no roots. And in particular, the implication geometrically is that its graph does not intersect the x-axis. Okay, all of this is to go back now to this thing here, and we learn that x squared plus 3, there's no zeros. So the only time that this numerator can be 0 is at x equal to 0. Yeah? Great. What about the denominator? X squared minus 1 cubed. When is the cube of something 0? Well, the only way the cube of something is 0 is if that something is 0. Rewind 10 seconds if that didn't make sense to you. When is x squared minus 1 0? Well, x squared minus 1, set it equal to 0. Add 1 to both sides. Take the square root of both sides. You get the absolute value of x is equal to 1. Therefore, x is equal to plus or minus 1. Plus or minus 1. So we have 2 points where the denominator is 0, plus and minus 1. Those are discontinuities of the function. The function is not even defined there. And we have a 0 of the function, a proper 0 of the function, namely at x equals 0. Okay, so there's the result. You see where my mouse is? -1, 0, and 1. Hopefully you're writing this out for yourself, honestly, because when you write things out, it sticks in your brain better. Next, we're going to cut up the real number line. There's the real number line into subintervals, using as the cutting points the points that we found in the previous step. We found 3 points in the previous step: -1, 0, and 1. And you can see I've dotted those boldly with dark dots. This cuts up the real number line into 4 pieces. 1, 2, 3, 4. Step 3, I'm going to pick test points in each subinterval. So I've done that in this picture here. You see these white solid circles here, 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 and here? These represent each one choice from each of the subintervals. Now, I have to emphasize, these are choices that we are making, but it doesn't matter what choice you make. I could have, instead of choosing, for example, -2, I could have chosen -200. I just need to pick something from this interval, from negative. Oh shoot, this is poorly written here. This is very confusing. This should read -infinity to -2. I don't know what happened here. I must have been intoxicated or something when I wrote this. -infinity to -2. In fact, can I quickly change this? Visual Studio Code, curve sketching. Let me quickly change this. Control Shift V so I can see this guy here. Let me quickly change this. Go to this place right here. Yes, here we go. So this should really read -infinity to -2. And when I compile this, this should magically change on our stream. Did I compile it? Oh, it's taking a little bit to build. There we go. Okay. Good. I fixed it. So I picked test points in each subinterval. You see, the basic idea, just for if you're interested in why this all works, is that the only possible places where f could change sign are at these 3 black points. I'm not guaranteeing that it does change sign. These are the only places where it could. And the reason is because h, so did I say f? H here is a continuous function. It's continuous on its domain. It's got discontinuities, but it's continuous on its domain. So if you think about drawing a continuous function, the only way that you can change sign is if you cross the x-axis, that's corresponding to being a 0, or if you lift your pen up and then drop it back down again. That corresponds to being a discontinuity. Okay. So I picked 4 test points. And now what I'm going to do is shove those test points in to the function and test for sign. SIGN. Now, evaluating a function at a particularly complicated function can be quite numerically laborious. And I don't like arithmetic. If I don't have to do it, I'd rather not. But in this case, it's relatively easy to analyze what's going on because this thing is nicely factored. So for example, at -2, which is my first test point here, if I plug that in, look at this first factor, 2x. Do you notice that its sign is going to be negative? In fact, let me do this on paper it's less awkward if I do it on paper. So we have this function here, h of x equals 2x times x squared plus 3 divided by x squared minus 1 squared, cubed rather. And what we did is we found all the zeros. The zero is, there's only one zero, namely at 0. And we found the places where it's discontinuous, negative 1 and 1. And then we picked inside of each of these subintervals, and there are 4 subintervals. The 4 subintervals are from negative infinity up. Oh my goodness, what have I done? Yeah, I messed up on the worksheet again. Let me fix this again. I wrote from negative infinity to negative 2. This should read negative infinity to negative 1. Man, I really am. Okay, never mind. I'm okay. Everything's great. Let's just build it and fix it. There we go. I fixed it. Okay. Returning back to here. This is from negative infinity to negative 1. That's that interval. This is from negative 1 to 0. This is from 0 to 1. And this is from 1 to infinity. Okay. And what I've done is picked a test point from each of these subintervals. I'm going to label those in green here, like this. And I bet you can guess what they are. They are negative 2, negative 1/2, 1/2, and 2. Those are just the easiest numbers for me to work with inside each of these subintervals. Now, what I have to do is evaluate h at each of these test points. So I have to compute h of negative 2. I have to evaluate h of negative 1/2. I have to evaluate h at 1/2. And I have to evaluate h at 2. And that looks like a lot of work. However, what I can do, instead of thinking, because I only care about the sign, I don't actually care about the value of these 4 numbers. I care about their sign, their SIGN, whether they're positive or negative. So what I can do is break up the calculation using the factorization that I've got here. So for example, I know that when I plug negative 2 into 2x, I'm going to get a negative number out. So I'm going to just denote that state of affairs like this, maybe a negative, and sometimes I like to put a circle around it. That means negative. Then I have a negative times what I get by putting negative 2 into x squared plus 3. Now remember x squared plus 3, we took that parabola, we lifted it up 3 units. Do you notice that the y coordinates of the points on that parabola are always positive? That means x squared plus 3 is always positive. And then if I put negative 2 down here, well, negative 2 squared is 4. 4 minus 1 is 3. You cubed a positive, and that's a positive. So this ends up being a positive downstairs. So we have a negative times a positive divided by a positive. Don't you agree that this is negative? Yeah? Does this make sense? Hope so. And we can continue in this way. And notice I didn't have to evaluate precisely the value of these numbers, just the sign. I might even write, something like this, equals negative. It's a little bit whatever. How about here? H of negative 1/2. Well, here I get something negative, then I get something positive. But then what changes is that down here, negative 1/2 squared is small, it's 1/4, and 1/4 minus 1 is some negative number. And when you cube a negative number, you again get a negative. So here I have negative times positive times negative. This is again, or not again, but this is now positive. And we could write this state of affairs like this, positive. You do it with h of 1/2, and what you're going to find is that you have positive and then positive divided by negative. So this ends up being negative. And for h of 2, I think everything inside is positive, which is greater than 0, and this is positive. Okay? Based upon the sign of the function at these test points, we conclude the sign of the function on the entire subinterval. So for example, the fact that h is at negative 2 is negative this means that h is negative on the entire subinterval from negative infinity to -1. In other words, by evaluating the sign of h at one point, we get to deduce the sign of h on an entire subinterval. This subinterval. Here, the fact that h is positive at -1/2 means that h is positive on the interval from -1 to 0. This fact implies that h is negative on the interval from from 0 to +1, and this fact implies that h is positive on 1 to infinity. And this is the complete sign analysis. This is the output of the sign analysis. And this is a fine way of presenting it. That's a lot of writing. Maybe one way of saving yourself some work is to use the union symbol. So you could also say h is negative on the interval from negative infinity to -1, union 0 to 1. That is like an uppercase U looking symbol. H is positive on the interval from -1 to 0, union 1 to infinity. These are both completely acceptable answers. Okay, let's see if we got the same thing in my document here. And yeah, so you can see I've computed the signs at the test points, and then I conclude that h is positive, again, on the entire subintervals that contain these test points. That contain these test points. Yeah. Okay, that's sign analysis. And I said I wasn't going to do sign analysis because I claimed that I did sign analysis yesterday. But I think going into it with a little bit more detail here today is helpful. Okay. Here I go into detail about this function. Okay. And here I ask you. Okay, so this is an interesting function because it's the one that we studied during Wednesday's lecture. You know what's awkward about this? Okay, I keep stumbling over my words because can I tell you the reality of the situation just to hurt your feelings a little bit? In fact, today is Tuesday. Like right now, it is Tuesday for me. But I'm pretending that I gave a lecture on Wednesday, namely tomorrow morning, that I haven't given. And that's fucking with me a little bit, okay? And so I apologize if I'm stumbling over myself. Anyway, so if you have this function, x squared minus 3 times e to the x, here's f prime of x. And hopefully we did that yesterday. And we analyzed the sign of f prime. In part A, I'm asking you to compute the derivative, the second derivative. The second derivative, it turns out, is is by definition the derivative of the derivative. So to complete part A of this problem, you would take the derivative of this function, and what rule would you use? You would use the product rule, of course. Then I want you to do a sign analysis of the second derivative. Okay? That's here. And when I say that your answers for step 1 should be these numbers, what I mean is that the step 1 of your sign analysis, where you're trying to find the zeros of the function and the places where it fails to be continuous, those should correspond to these points here. And I'm pretty sure you're going to need to use the quadratic formula to find those roots. Okay, so have fun with that. Why do I ask you to do a sign analysis of f double prime? Give me just 30 seconds. Because it turns out that much like the fact that we just learned today, that the monotonicity of f is determined by the sign of f prime, it turns out that the sign of f double prime determines something about f. What is that something? It's called the concavity of f. And that's what we're going to learn next in this section. We're going to learn about concavity. But I noticed that this video just passed 50 minutes, so I'm going to stop here. This again will air on Thursday. Feel free to watch it as many times as you wish. But yeah, we're going to continue on in this exciting journey into studying how the derivatives of a function inform you about the original function. This is very important. Okay, that's enough for now. Love you. Have a great weekend. I will see you on Monday. Tuesday is going to be a holiday. Okay, it's going to be Veterans Day. And what I am thinking is that we will have a midterm on the Thursday of that week. I might move it to Monday. So I'm jiggleable on this. It really is going to be determined by how well we get through this material. So if you want to see the midterm on the Thursday instead of the Monday, please study the stuff really well and be responsive to questions when I ask you them in class. Okay? All right. Love you. Bye.